When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. Our magnetic compasses would all point the wrong way. We'd need to update our maps. Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before, and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal, and based on fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore the science behind geomagnetic reversals and find out whether the next one will be an apocalyptic scenario or whether it'll lead to nothing more than a few lost birds. What truly happens when things go south? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The two planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there. The temperature drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core's spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical south. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, it would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter timeframes. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably. But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree. It would take far longer than 10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. The Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's what we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Lachamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet, but while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand. Think you know Jupiter? Think again. For decades, scientists argued over what the core of our biggest gas giant was like. Was it solid or missing altogether? Then, in 2017, NASA's Juno mission made that debate irrelevant overnight. The data from Juno suggested both sides were wrong, and revealed a third option no one expected. Jupiter's core isn't solid, but it isn't absent either. It's fuzzy. And that's a problem, because it upends everything we thought we knew about Jupiter's formation, its interior, and even its bizarre magnetic field. I'm Alex McColgan, and you're watching Astrum. Join me today as we uncover exactly what Juno found, explore how a fuzzy core could form in the first place, and reveal why this changes how we think not just about Jupiter, but gas giant planets everywhere. For decades, two competing theories dominated the scientific conversation around Jupiter's core. Many supported the gravitational collapse theory, which suggests that Jupiter formed directly from the collapse of a gas cloud under its own gravity. This would have happened in the colder, outer reaches of the solar system before Jupiter migrated to its current location. In this scenario, the gas giant would have no core at all. It would simply be a layer cake of churning gas all the way through. But this theory didn't have the whole scientific community convinced. Others were almost certain Jupiter's core was solid, made up of heavy elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. As this solid core grew larger and larger, its gravity started capturing more hydrogen and helium, swirling it together over millions of years to form the planet we all recognize today. Intuitively, this seems to make sense. Our solar system formation models suggest giant planets could be created this way, since ice and rock would condense first in the outer solar nebula, capturing gases in their gravity as they migrated inward. This theory, known as the core accretion model, predicted a dense, well-defined core with a clear boundary separating the compact center from the surrounding layers of gas. To resolve the debate, early missions to Jupiter all took their turn trying to discern what lies beneath the red giant's dramatic atmosphere. By the 1990s, scientists knew that Jupiter was rich in heavy elements, implying the planet was made of more than just hydrogen and helium. The Galileo mission also found evidence that Jupiter's magnetic field must somehow be generated by liquid, metallic hydrogen in its interior. But if the core is purely liquid, how did Jupiter form in the first place? The standard theory of planetary formation requires a solid nucleus to start gas capture. If Jupiter once had such a core, but somehow lost it, how did that happen? Could everything we know about how gas giants form be completely misguided? Despite the successful missions to Jupiter, the planet's structure remained a mystery. The data gathered wasn't precise enough to determine whether its core was solid or diffuse, what it's made of, or how exactly it generates such a massive magnetic field. But that all changed with Juno. On the 5th of August 2011, NASA's Juno mission launched from Cape Canaveral in Florida. Its main objective was to get closer to the truth of Jupiter's composition by measuring its gravitational and magnetic fields with unprecedented precision. Unlike Galileo, Juno was purpose-built to map the planet's gravitational field in great detail, about 100 times better than previous maps. When it entered orbit on the 4th of July 2016, it began tracing a highly elliptical polar orbit, swooping down within just 4,200 kilometers of Jupiter's cloud tops. It did this again and again, from several angles, a path that made this probe incredibly sensitive to tiny changes in Jupiter's gravity. But why are we interested in gravity in the first place? What does that have to do with figuring out what Jupiter's core is made of? Well, we've all seen gravity depicted like this, a perfectly round cone, the same on all sides. I'm sorry to tell you, this diagram is a bit of an oversimplification. for a planet's gravity to be completely uniform like this, the distribution of mass inside it would also have to be perfectly uniform. In reality, if you zoom in really close, their gravitational fields look a little more like this. Planets are made up of many different elements and materials, each with their own masses, densities, and distributions. These differences are reflected as tiny, almost imperceptible variations in a planet's gravitational field. That's why Earth's gravitational field is actually slightly different over mountains than plains, and why scientists are so fixated on mapping Jupiter's gravitational field with incredible precision. As Jupiter's gravity fluctuates, it causes Juno to speed up or slow down. This spacecraft is so precise, it can detect changes in speed as subtle as 0.01 millimeter per second. At the same time, Juno is continuously beaming a steady radio signal back to Earth, which scientists can decode using the Doppler effect. Where gravity is stronger, Juno accelerates, and we perceive a higher frequency wave, while a deceleration due to weaker gravity would result in a lower frequency wave. By repeating this over and over, scientists can build up a very precise map of Jupiter's gravitational field, which directly reflects how its mass is arranged inside. While the Galileo mission managed to paint Jupiter's gravity in very broad strokes, Juno brought it into razor-sharp focus. And what it revealed about Jupiter's core caught researchers by surprise. Turns out, both theories about Jupiter's core were wrong. It seems to have a core, but it isn't solid like we thought. It's fuzzy. Instead of a dense, compact ball, it's dilute, gradually blending with the hydrogen-rich layers above it. It doesn't appear to have any sharp boundaries. It's also much wider than expected, spanning about half the radius of Jupiter itself. The findings quickly sparked a flurry of questions, including whether our understanding of how Jupiter formed needed a refresh in light of this exciting new data from Juno. A popular theory soon emerged to explain this unexpected discovery, that Jupiter once had a solid core to begin with, but a catastrophic collision in its early history shattered and scrambled it in with the surrounding lighter gases to give us the fuzzy core we see today. The only problem is, our standard model for how giant planets like Jupiter form doesn't work without a solid core. So either Jupiter's fuzziness somehow developed later on, or our models are wrong. Anyway, for such a dramatic shattering to occur, the collision must have been massive, possibly with another young planet. Scientists speculate that up to half of Jupiter's core could have originated from the remains of this planet. It was a neat enough theory, except for one unexpected hiccup. A curious team of researchers tried to model this giant collision using a supercomputer. They wanted to emulate the exact event that would lead to the results Juno showed us. So they designed several possible scenarios of a massive object colliding with a Jupiter-sized planet and ran multiple simulations, varying the size of the Jupiter protoplanet and the angle and speed of collision. But try as they might, they couldn't find an event that led to the fuzzy core Juno showed us. Every time they tried, the models did the same thing. The impact would initially rock the planet to its core, but after a while, the dense, rocky material would settle back down again, like sediment at the bottom of a glass. It didn't dissolve into the rest of the planet. A sharp boundary would reappear, clearly separating the core from the outer hydrogen layers. It didn't fit the Juno data, so it was back to the drawing board. Funnily enough, the next clue in this puzzle didn't come from Jupiter at all. It came from its next door neighbor. Well, that is, if you consider 648 million kilometers away next door. We've known since 2014 that the waves in Saturn's rings are caused by vibrations inside the planet. This gives us an insight into what the planet's core might look like, similar to how earthquakes let us study Earth's interior. When researchers paired Cassini's gravitational field data with these wave measurements, it painted a staggering picture. These observations show that at least some of Saturn's deep interior doesn't convect. This is a big deal. Inside a giant planet like Saturn, heat is constantly trying to escape. Normally, that happens through convection. It's what is constantly happening in Earth's mantle, or when you heat up a soup. Hot fluids rise to the surface, cool, and then fall back down, only to be heated up and rise again. On and on it goes. If Saturn were fully convective, it would mix heavy elements throughout its interior. There wouldn't be a dense central region at all. The whole thing would be a fully mixed, homogeneous soup. But if it were partly stable against convection, we'd expect to see a gradient of material, with heavier elements concentrated towards the center and tapering outward. And that's exactly what the data shows. Researchers published their findings in 2021, arguing that the only way to explain Saturn's ring wave data, gravitational field data, and partial lack of convection is that it too has a fuzzy core. As it happens, Juno data also suggests large regions of Jupiter may not be convective. We seem to be slowly connecting the dots. If Saturn and Jupiter have fuzzy cores, they likely stem from a common denominator rather than a random collision event. Now, scientists are working on a new, emerging theory of how the gas giants came to be, one in which fuzzy cores are a natural part of planetary formation. We haven't arrived at a neat explanation yet, but it is clear that the old assumptions we had about the largest planets in our solar system are incorrect. Jupiter and Saturn are not made up of solid core and gas envelope, nor do they have a completely mixed interior. Their fuzzy cores are made up of a compositional gradient, with more heavy elements concentrated in the center, which dissolve out into the gas envelope without a clear boundary. This complexity and uneven mixing challenges our current models for planetary evolution. Where our old, simplistic model predicted the giants would cool predictably over time, these new models don't follow the same patterns. And the same is true for all the gas giant exoplanets we've discovered and studied so far. But in the meantime, there is one other jigsaw piece that needs to fit the puzzle created by Jupiter's fuzzy core: its weird and wacky magnetic field. For years, scientists have known that Jupiter's magnetic field is generated through a dynamo process in its metallic hydrogen layer. This layer spans 20 to 60,000 kilometers deep, where temperatures can exceed 30,000 Kelvin and pressures are millions of degrees greater than on Earth's surface. Under these extreme conditions, hydrogen is in a liquid state, but even more incredibly, here, hydrogen's electrons become delocalized or free-flowing. This creates an electrically conductive metallic state. Coupled with Jupiter's fast rotation, this metallic liquid hydrogen creates a dynamo effect, though the exact process of how it's powered remains a mystery. Whatever it's doing, it's working. Jupiter has the largest, strongest magnetic field of any planet in the whole solar system. Its magnetosphere spreads 7 to 21 times the diameter of Jupiter, tapering into a tadpole shape behind it that extends into Saturn's orbit, about 1 billion kilometers away. However, Jupiter's magnetic field also has some quirky characteristics. It's much stronger in the northern hemisphere than the southern hemisphere, has intense, localized magnetic spots, and 2 magnetic south poles. Scientists hoped Jupiter's fuzzy core might actually explain some of these strange behaviors. Frustratingly for them, the opposite turned out to be true. Jupiter's fuzzy core actually complicates rather than explains its magnetic field. Magnetic fields in planets are usually created by swirling motions of electrically conducting material, like the metallic liquid hydrogen in Jupiter's core. However, Juno data showed that large regions of Jupiter, like Saturn, seem to be at least partially non-convective. Researchers modeled the fluid dynamics of Jupiter's interior in two potentially non-convective regions to see how they would affect the magnetic field, one in the upper part of the planet's interior and the other lower down, corresponding to the dilute core. They concluded that the upper stable layer helps explain Jupiter's magnetic field even better than previous solid core models. However, the lower region, representing the non-convective dilute core, did not explain Jupiter's magnetic field on its own. In other words, a completely stable fuzzy core produces a magnetic field that's very different from the one we actually observe. Now, researchers believe Jupiter's dynamo is more complicated than originally thought. It's possible that below the uppermost molecular hydrogen layer, Jupiter has a layer of helium, which rains down through the liquid hydrogen, like oil passing through water. Some think this could have an effect on the magnetic field. Another theory claims Jupiter's dynamo doesn't operate in a homogeneous way like it does on Earth, and that instead, the planet's lopsided magnetosphere is the result of variations in density, electroconductivity, or both. But on the whole, no one knows exactly how this magnetic field is produced, or what role the fuzzy core plays in its creation. One thing we do know for certain though, is Jupiter's magnetic field is responsible for the biggest, brightest auroras in the solar system. On Earth, auroras are only visible for a 4 to 6 month window. On Jupiter, they never stop, covering the poles with a dazzling display of colour hundreds of times more powerful and energetic than the auroras we're familiar with. By stringing together far UV images from Hubble's imaging spectrograph, scientists were able to create these videos of the auroras in action. Aren't they spectacular? Despite Juno's discoveries, Jupiter keeps its secrets close to its chest. We still don't know how its fuzzy core actually formed, nor do we know how permanent it is. Is the fuzzy core a stable structure that will endure for billions of years? Or is it slowly dissolving into Jupiter's gaseous layers? What relation does it have to the metallic hydrogen above it, and the resulting magnetic field Juno mapped? Are fuzzy cores just a natural part of gas giant formation? We can't say for certain yet. But one thing's for sure, our current models don't show the full picture. Hopefully with further study, we'll slowly be able to answer these questions one by one. Though, the more we learn, the more questions we'll keep asking. The pursuit of truth is relentless, and it is also perhaps the most human thing we can do. Imagine standing on a quiet hill, watching the sky burst into a symphony of colours as the sun peaks above the horizon. It's a daily spectacle that many of us take for granted. The warm hues of orange, red and pink splashing across the sky. Yet, this beautiful sunrise is only the final chapter in the light's long journey. If we trace the path of these photons from their endpoint in the retina at the back of your eye, through the Earth's atmosphere, across the 150 million kilometer void separating our planet from its host star, and finally through the varied and tumultuous layers of that star, we discover the source of the warmth on your face and the colors painted across the sky. The sun's core, a nuclear engine that has been raging for 4.5 billion years. Born in a cosmic nursery from the remnants of ancient stars, the glowing sphere of searing plasma that dominates our sky is the product of complex forces that have played out over millennia. So let's take a journey back in time, tracing the origins of the sun, exploring its intricate layers, and mapping the elements that make up its very structure. I'm Alex McColgan, and you're watching Astrum. Join me as we dive into the depths of our sun and learn what secrets lie behind the blinding curtain of light and time. To understand how the sun formed, we must go back to before our solar system even existed, about 4.6 billion years ago. At that time, in a relatively quiet region of the Milky Way galaxy, a massive cloud of gas and dust, known as a giant molecular cloud, drifted silently through space. This was no ordinary cloud. It was immense, possibly spanning hundreds of light years across, with a mass equivalent to millions of suns. Within this cloud lay the scattered remnants of ancient stars that had long since exhausted their nuclear fuel and exploded as supernovae, casting their enriched contents into the cosmos. This stellar debris included a mix of elements such as hydrogen and helium, the building blocks of stars, along with heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements made this molecular cloud fertile ground for forming new stars and planetary systems. However, such a massive cloud requires a trigger to initiate the cascading collapse that results in stellar birth. Scientists believe that this trigger could have been a shockwave from a nearby supernova explosion that compressed parts of the cloud, causing it to fragment and collapse into regions of higher density. This collapse marked the beginning of the pre-solar nebula, the dense region within the molecular cloud that would eventually give birth to our solar system. Some scientists have even proposed a name for this hypothetical exploding star, Coatlicue. Named after the Aztec goddess of earth and fertility, Coatlicue symbolizes the death and rebirth cycle, where in this case, the death of one star can seed the formation of new ones. As the gravitational collapse of the giant molecular cloud progressed, it did not result in a single massive object, but rather fragmented into multiple dense clumps. This fragmentation occurs due to a phenomenon known as Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is a critical distance within a cloud at which the forces of gravity are balanced with the natural internal gas pressure that keeps the cloud propped up. When a defined section of the cloud exceeds the Jeans length, it will collapse in on itself. Different regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently to form multiple protostellar cores, as opposed to one single massive body. The protostellar core was the earliest phase in our sun's life that was recognizably star-like, crunching itself into a tighter and tighter sphere by the ever-clenching fist of its own gravity. The core is surrounded by infalling gas and dust. As more material accumulates, the core becomes denser and hotter, setting the stage for the next phase of star formation, the protostar. Once a protostellar core becomes sufficiently dense and hot, it evolves into a protostar. The central region has heated up to the point that it begins to emit light and heat from the energy released by gravitational contraction. But its core has yet to reach the temperatures required to ignite nuclear fusion in the core. As the protostar continues to accumulate material and grow in mass, the pressure and temperature in its core increase dramatically. Our sun developed through this embryonic state of contraction and heating for millions of years, before eventually building up its core temperature to about 10 million degrees Celsius, at which point hydrogen nuclei began to fuse into helium. And with that, the sun was born. At this stage, the innate angular momentum of the surrounding material that shrouds the infant star generates rotation. A cloud of this size will always have some slight rotation, nothing in the universe is still, and conservation of angular momentum dictates that the cloud must spin faster and faster as it crunches down into tighter space, similar to how a spinning figure skater speeds up as they tuck in their arms. Around the equator of rotation, some of the material is moving fast enough to stay in orbit, but higher up and lower down, the momentum is insufficient to resist the protostar's ravenous pull and falls helplessly into its jaws. And so, the cloud flattens out into a disk, a protoplanetary disk. This disk is a cosmic lottery. As it cools and coalesces, planets, moons, asteroids, and comets will be relentlessly created and destroyed. Some material will be robbed of its momentum and tumble into the sun, while neighboring matter will go on to become part of the many bodies that make up our solar system today. With its new ability to fuse hydrogen atoms into helium, the sun could finally generate energy to push back against the forces of gravity that sought to squeeze it further. The energy streaming out of the fusion reactions created an outward radiation pressure that balanced the inward gravitational pull of the gas, allowing the young star to achieve a stable state known as hydrostatic equilibrium. In this state, the star no longer contracts under its own gravity, and it enters a stable phase of its life known as the main sequence. This balancing act between internal pressure pushing outward and gravity crushing in is the axis that defines every stage of the sun and all stars' lives. We saw it during the initial collapse, and here as it settles into a stable main sequence star, and it will be the pendulum that eventually swings towards its dramatic death. For now, let's unpick the process of nuclear fusion and how it's capable of keeping an object as massive as the sun stable and steady for billions of years. To understand how nuclear fusion occurs in the sun, we need to examine extreme conditions present within its core. Today, temperatures reach around 15 million degrees Celsius and pressures more than 250 billion times that of the Earth's atmosphere. In this blazing cauldron, hydrogen atoms are stripped of their electrons, forming a plasma composed of free protons and electrons. Under such intense conditions, these protons, normally repelled by their shared positive electric charges, are forced into extremely close proximity. The force that usually keeps them apart is the Coulomb force, an electrostatic repulsion between positively charged particles. It's exactly the same force that resists as you try to push the same ends of a bar magnet together. Overcoming this force is the primary challenge for nuclear fusion to occur. Despite the extreme kinetic energy of protons in the sun's core, most collisions are still not energetic enough to overcome the Coulomb barrier. Under normal conditions, protons need immense energy to get close enough for the strong nuclear force to bind them together. This barrier is so significant that physicists around the early 1920s, using a classical understanding of how particles interact with each other, determined that fusion should not occur at the temperatures and pressures found in the sun's core. To solve the puzzle, we needed a scientific model that has come to explain many of the seemingly impossible phenomena we observe in the universe: quantum mechanics. The quantum mechanics revolution of the 1920s introduced the concept of particles behaving both as particles and as waves. One of these phenomena is quantum tunneling, where particles have a certain probability of tunneling through a barrier even when they lack the classical energy needed to overcome it. In the sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without having to climb over it in the classical sense. Even though these protons do not have enough kinetic energy to overcome the electrostatic repulsion directly, quantum mechanics gives them a chance to appear on the other side of the barrier. To visualize this process, consider a diagram of the Coulomb barrier. In the diagram, you will see a high energy barrier representing the repulsive electrostatic force between two protons at varying distances. The energy needed to climb over this barrier is represented as a peak. The calculations of a classical physicist would require the sun to have temperatures high in the billions of degrees Celsius, thousands and thousands of times higher than the sun's core, to hurdle this barrier. But quantum mechanics allows for the probability wave of a proton to tunnel through this barrier, appearing on the other side without ever going over the peak. This tunneling effect is what enables fusion to occur in stars like the sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through the Coulomb barrier, it gets close enough to another proton for the strong nuclear force to take over. The strong nuclear force, which is far more powerful than the Coulomb force, operates only at very short ranges, on the order of femtometers, where 1 femtometer is equal to 10 to the power minus 15 meters, roughly the size of a single proton. The strong nuclear force binds the protons together, but this is only the first step in a series of nuclear events known as the proton-proton chain. The proton-proton chain reaction is the dominant fusion pathway in the Sun and other stars of similar size, accounting for roughly 99% of the Sun's energy production. It starts with 2 free-roaming protons combining to form deuterium, a heavy isotope of hydrogen, along with the emission of a positron and a neutrino. This step is rare but essential, as it allows the fusion process to continue. The deuterium then rapidly fuses with another proton to form helium-3, releasing a high-energy photon, a gamma ray. In the final step, 2 helium-3 nuclei collide and fuse to form helium-4, releasing 2 protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is another pathway at play, particularly in stars hotter and more massive than our Sun. This pathway is known as the CNO cycle, short for carbon, nitrogen, oxygen. In this cycle, carbon, nitrogen and oxygen nuclei act as catalysts to fuse protons into helium. The CNO cycle is more efficient at higher temperatures and only contributes a small percentage of our Sun's energy output. The energy produced in these fusion reactions comes from a small amount of mass being converted into energy, as described by Einstein's famous equation E equals mc squared. In the fusion process, the mass of the resulting helium-4 nucleus is slightly less than the combined mass of the original 4 protons. This missing mass is not lost, but rather converted into energy that radiates outward from the Sun. Every second, the Sun converts about 4.3 million tons of its mass into energy. That's right, the Sun is losing mass all the time. To put this into perspective, this is the equivalent of the mass of about 3 million cars being turned into pure energy every second. This is the energy that ultimately powers the Sun and provides the light and heat that reaches Earth. But before these photons pouring out of these reactions can reach the Earth and everything else in the solar system and beyond, they must first escape the 700,000 kilometers of chaotic solar interior that lies above them. To truly grasp the complexity of the Sun and its stratified layers, let's follow a single photon, a particle of light, from its creation within a proton-proton reaction all the way to the surface. This journey is anything but straightforward. In fact, it will take thousands, if not hundreds of thousands of years for this photon to complete its journey, passing through several distinct layers of the Sun, each with their own unique properties and behaviors. As we've already found out, our photon's journey starts in the core, a region that spans about 25% of the Sun's radius, but holds nearly half of its total mass. And, as we've also heard, the core is incredibly dense, at around 160 grams per cubic centimeter. It's over 20 times denser than iron. To put that into perspective, if your phone was made of material that dense, it would weigh as much as a heavy-duty sledgehammer. For our photon, this means that the environment is so tightly packed with particles, it cannot travel far before being absorbed by a neighboring particle. Of course, not long later, that particle will pack the photon's bags and send it out into the melee of the core for another particle to catch and release in some other random direction. It's a bit like trying to navigate through a dense crowd, where every few steps you bump into someone and have to change direction. This constant interaction of absorption and re-emission is what gives the core its chaotic nature, resulting in a journey for a photon that is more of a random walk than a direct path outward. This random movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, fast-moving molecules. And there is no preference for the direction that a photon could fly back out of a particle that had just absorbed it. In theory, a photon could make it all the way to the surface of the Sun before random chance directs it back towards the core. To add to the complexity, as photons are continuously absorbed and re-emitted, the energy gradually decreases from gamma rays to X-rays and eventually to visible light as they move towards the Sun's outer layers. Understanding the processes occurring within the Sun's core has been a challenging endeavour for astronomers. The core is completely obscured by the outer layers of the Sun, meaning we cannot directly observe it through any form of light. Instead, scientists have developed ingenious methods to infer the dynamics of the roaring inferno below. One of the key techniques is the study of helioseismology, the observation of waves rippling across the Sun's surface. Just like seismologists study earthquakes to understand Earth's interior, helioseismologists measure the vibrations of the Sun's surface caused by sound waves that travel through its interior. These sound waves are influenced by the temperature, density, and composition of the Sun's layers, allowing scientists to construct models of what is happening deep within. Solar neutrinos, elusive subatomic particles that I've talked about in a previous video, are also released during the fusion reactions in the Sun's core. Neutrinos interact so weakly with matter that they can travel straight out of the Sun in just 2 seconds, hardly aware of the tangle their photon counterparts are caught up in. For decades, solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists discovered that neutrinos change their properties, or flavors, on their journey to Earth, that the mystery was resolved, confirming both our understanding of particle physics and the nuclear processes in the Sun's core. Next, the photon enters the radiative zone, which extends from the edge of the core to about 70% of the Sun's radius. Here, temperatures gradually drop from 15 million degrees to around 2 million degrees Celsius. The density of matter also drops, going from around the density of gold in the zone's depths to less than water near the top. The dominant energy transportation method is still this frenetic process of photons skittering through the layer, carrying their energy on average towards the surface. And as the density of the plasma continues to decrease as we move outward, our photon has slightly more wiggle room, capable of bigger leaps between interactions. But even here, outside of the core, the Sun's material is still so opaque that even a few centimeters could block out as much light as hundreds of meters of water. We are able to envision such precise models of the Sun's interior because of models like the Standard Solar Model, or SSM. It is a mathematical framework based on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer. Essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a place out of our reach. The SSM models how energy is passed between particles in its complex equations, describing how photons are transported through the dense plasma. This allows us to calculate how transparent the solar material is to radiation at different temperatures and densities, and from there we can work out where the radiative zone ends and the next layer begins. This is one of my favorite things about mathematics. It allows us to explore environments that we can never visit, almost like how quantum tunneling allows protons to jump over the Coulomb barrier and produce the photons we are now following. As our photon approaches the upper boundary of the radiative zone, it enters the tachocline, a thin, transitional layer where the radiative zone meets the next layer, the convective zone. The tachocline is an environment of extreme contrast, where the relative uniformity of the radiative zone meets the boiling, bubbling convective zone. The strange conditions in this extremely thin layer likely plays a key role in the solar dynamo that generates the Sun's magnetic field. The tachocline is thought to twist and amplify the magnetic field, shaping the sunspots and solar flares that define the star's surface. Zipping through the thin tachocline, our photon arrives at the convective zone. Stretching out from about 70% of the sun's radius to just beneath the visible surface, the photosphere, the temperatures have dropped to below 2 million degrees Celsius. Now, the sun's plasma is no longer dense enough to effectively transfer energy by radiation. Instead, the plasma becomes unstable and begins to move in massive convection currents, much like boiling water in a pot. Hot plasma rises towards the surface in large cells called granules. These granules, with diameters of thousands of kilometers, surge upward under their power of buoyancy at speeds of hundreds of meters per second, like a beach ball that you force below the water, rushing to the surface as it squirms from under you. The force required to move this volume of matter against the sun's gravity is astonishing. Imagine the force of 10 billion hurricanes, and you'd be just starting to get close to the energy necessary. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rolling waves of plasma that churn vigorously. I have explained these convection cells and the beautiful hypnotic patterns they create on the sun's surface in a lot of detail in this previous video. This is a significant change in how energy is transported. While photons still interact with particles, the primary mechanism of energy transfer in the convective zone is no longer the random absorption and re-emission between particles, known as radiative diffusion, but rather the movement of hot plasma rising and cooler plasma sinking. This convection motion carries the energy outward more efficiently than in the radiative zone. Upon reaching the top of the convective zone, the photon is carried to the photosphere, the sun's visible surface. Temperatures have now cooled to about 5,500 degrees Celsius, and the plasma has thinned enough for photons to escape without being constantly reabsorbed. It is from this thin, roughly 500 kilometer deep layer that the light we see from the sun is emitted. Above them lies only the sun's corona, which is itself a fascinating environment, but only around a billionth of the density of the photosphere, and therefore not much of an obstacle to our photon. It is incredible that an object like the sun, that many refer to as a ball of gas, can have such a sharp boundary. But the photosphere is where our photon finally breaks free, traveling at the speed of light and beginning its journey across the vastness of space. Our neutrino friend that was created at the same time? It's long out of the Milky Way by now. Since settling into its stable main sequence phase, nuclear fusion has altered the strength of the sun's layers, gradually increasing its brightness over billions of years. This is because the fusion process inevitably leads to changes in the composition, density, and temperature of the sun's core, which in turn affects the overall behavior and the future of our star. As hydrogen fuses into helium, hydrogen gradually depletes in the core, and helium ash begins to build up. Unlike hydrogen, which readily undergoes fusion at the sun's current core temperatures, helium requires much higher temperatures to fuse. As the abundance of helium increases, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and as more helium collects in the core, the overall density increases. At the same time, because helium is not fusing and creating energy, it does not contribute to the outward radiation pressure that counterbalances the sun's immense gravitational pull. The result is that gravity will begin to dominate, causing the core to contract further. To prevent collapse under its own gravity, the sun must increase its core temperature as helium builds up. The hotter core turns up the dial on hydrogen fusion because nuclear fusion rates are extremely sensitive to changes in temperature. This increase in fusion releases more energy, which results in a brighter star and temporarily restores the balance between gravity and radiation pressure. Through this process, the Sun's energy output has increased by about 30% over its lifetime, and this trend will continue for billions of years as long as hydrogen fusion dominates in the core. In the radiative zone, the layers have grown hotter and more opaque. The rising temperature of the core means more energetic photons are produced, which are more prone to interacting with the surrounding plasma and pinballing around. As a result, this zone has become less efficient at radiating energy outward, trapping photons for longer before they can continue their escape. The convective zone has also expanded slightly over time due to the increased energy production. As the Sun continues to burn through its hydrogen fuel over the next 5 billion years, its core will eventually be left overburdened with inert helium that can no longer sustain fusion under its own pressure. When this happens, the Sun will evolve into a red giant, dramatically expanding and engulfing its inner planets, including Mercury and Venus and possibly the Earth. In this phase, the core will contract and heat up until it ignites in a helium flash, starting the fusion of helium into heavier elements like carbon and oxygen, yet again swinging the pendulum between the relentless gravitational hammering and the resisting forces of energy from the core. This process will create new layers and cause the Sun to swell even further before shedding its outer layers to form a ghostly remnant, a planetary nebula. The core that remains will cool and fade, becoming a white dwarf, a dense, Earth-sized ember of a once raging fire. This transformation from a stable star to a red giant and eventually a white dwarf is a remarkable and complex process with many fascinating details, which we will no doubt explore in a future video. But ending our journey from the depths of the Sun's ancient past to its modern interior, let's return to that quiet hill where we began, watching the colors of sunrise. I hope the next sunrise you see becomes that little bit more special. I hope the pink and orange photons, scattered for one final time on the molecules of Earth's atmosphere before streaming through your pupils, will make you think of the incredible voyage they have endured, beginning with the collapse of a colossal cosmic cloud into an element-building furnace, struggling for hundreds of thousands of years through a melting pot of plasma to gift you with this beautiful scene. I hope this exploration has deepened your appreciation for that daily miracle we often take for granted. And there's still so much more to uncover about our closest star, from the formations it will undergo to the profound impacts it will have on our solar system's future. Thank you for joining me on this journey through space and time. If you found this journey as enlightening as our host star, please give the video a like and fuse it with your own thoughts down in the comments below. Thanks for watching. The universe is full of secrets, and some of the most incredible ones are hiding just beyond the reach of visible light. What if I told you that more than 1.5 billion unseen objects, from galaxies and newborn stars to some of the oldest stars in our entire galaxy, are sitting just out of reach of us, cloaked in cosmic dust? That's a little frustrating to think about, isn't it? Until now, that is. Because thanks to the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift the veil on these hidden wonders. For the first time in human history, we have a pretty comprehensive infrared map of the Milky Way, one that pierces through the obscuring fog of space to reveal an unprecedented view of our galaxy and what lies beyond. I'm Alex McColgan and you're watching Astrum. Join me today as we appreciate how this first of its kind map was made and take a look at some stunning images that reveal previously unknown stars across our galaxy. In September 2024, Vista published the largest and most detailed infrared survey of the Milky Way ever undertaken. Encompassing a 13-year period from 2010 to 2023 across 140 nights of observation, this project has captured around 200,000 images and generated 500 terabytes of data. That's the same amount of data as it would take to stream a 4K video for nearly 3 years straight. Vista is part of ESO's Paranal Observatory located in Chile, with its main focus being to map large areas of the sky. Using Vista's infrared camera, known as VirCam, the team was able to peer through the dust and gas that permeates our galaxy and uncover some of the Milky Way's most hidden places. Traditional telescopes allow us to view space in visible wavelengths, which range between about 380 to 700 nanometers. But Vista isn't like traditional telescopes. Instead of relying on visible light alone, Vista operates at infrared wavelengths between 900 and 1200 nanometers, allowing it to detect otherwise invisible objects like stars obscured by dust and cold brown dwarfs, also known as failed stars, which don't emit enough visible light to be seen with a traditional telescope. To get an idea of the difference between visible and infrared light, take a look at these two images of the Lobster Nebula, or NGC 6357, one taken in visible light and the other with Vista's telescope. We can see that in the infrared, the dust that obscures our field of view seems to disappear, revealing what look like hundreds of thousands, or maybe even millions, of previously invisible stars. The map was created through Vista variables in the Via Láctea, or VVV survey, Via Láctea being the Latin name for the Milky Way, and its companion project, the VVV Extended Survey, or VVVX. The data collected from these two companion projects that make up the Vista Infrared Survey have already led to the publication of more than 300 scientific articles. Unlike other recent space maps, this is one of the most detailed ones ever made. It's the first infrared survey to cover nearly 80% of the Milky Way's luminous mass, and provides the largest infrared catalogue ever made of our galaxy's central region. It allows astronomers to study our galaxy in finer detail than ever before. This survey gives us an accurate 3D view of the inner regions of the Milky Way, which were previously hidden by dust. It covers an area of the sky equivalent to 8,600 full moons, and contains about 10 times more objects than any previously published infrared map from 2012. Our Milky Way consists of a central bulge, a dense, bright, puffed-up collection of stars, with a flat disk of 2 spiral arms wrapping from the ends. This image shows the area of our galaxy that was mapped in the survey. The red squares mark the central regions of the galaxy, which were observed by the original survey, and then re-observed again by the extended survey. And the other square colors show areas that were only observed as part of the extended survey. From this image, you can see that these surveys have focused right on the central plane of our galaxy, spanning part of the disk and most of the nuclear bulge. But what has Vista revealed? Argentinian astrophysicist Dante Minniti, who led the survey project, said, "We've made so many discoveries, we have changed the view of our galaxy forever." And as much as I'd love to talk about all of them in this video, it's probably best I stick to some of the highlights. As part of the survey in 2015, Vista turned its attention to the star formation region of Messier 20, also known as the Trifid Nebula, which lies about 9,000 light-years from Earth. Viewed in visible light in this image, we can see a beautiful nebula, glowing pink from the emission of ionized hydrogen, and surrounded by a blue haze of scattered light from young, hot stars. The cloud of gas and dust is obscuring the star-filled space behind it. Now look at this second image taken by Vista's infrared camera. Peering beyond the clouds reveals a whole swarm of new stars. This image not only allows us to see through the Trifid Nebula, but by chance it revealed objects on the far side of our galaxy that had never been seen before. To their surprise, astronomers identified two faint, reddened objects as Cepheid variable stars. While they appear in the image to be just behind the edge of the Trifid Nebula, in reality they are very distant, about 7 times farther than the nebula that once helped to block them from our view. Cepheid variables are a type of bright star that is unstable. They brighten and fade over a period of a few days or a few months, depending on their brightness. The first variable star we ever identified in modern times was Omicron Ceti, also known as Mira. It had been described as a nova until 1638, when Johannes Halwoods observed it getting brighter and dimmer in a cycle that lasted 11 months. As for this pair of newly discovered stars, they are the only Cepheid variables that we have identified so far in this location, which lies beyond the central bulge on the far side of our galaxy. And they can be really useful too. You can think of them as a kind of cosmic yardstick that can be used up to distances of tens of millions of light years. If you know how long the star's pulsation period from bright to dim is, then you can infer its absolute brightness as well as its age. You can compare absolute brightness to the apparent brightness, that is, the amount of light that reaches Earth, so you have a measure of how distant the star is. With a few reference points like these, we can build up a real picture of the scale of our galaxy and beyond. Looking toward the galactic center, a team of astronomers and data scientists found even more candidate Cepheid stars, 655 in fact. They then sorted these into one of 2 classes, and found that 35 of these 655 stars were classical Cepheids, the younger of the 2. This was really exciting, especially since the galactic bulge was thought to contain mostly elderly stars that are at least 8 billion years old. Recording their pulsation periods, the team revealed that all 35 of these Cepheids were less than 100 million years old, and some of them may be as young as 25 million years old. To put that in context, our own sun is about 4.5 billion years old, so the youngest Cepheid has only been around for 0.6% of our sun's lifespan. The team's exploration of Cepheids culminated in another major discovery. By mapping the 35 classical Cepheids they found, the team was able to trace a completely new feature in the Milky Way, a thin disk of young stars that stretches right across the galactic bulge. Buried behind thick clouds, it had remained unknown in all previous surveys of the region. In revealing this structure, combined with the discovery of older Cepheids as I mentioned earlier, scientists have inferred that there has been continuous star formation along the midplane of the galaxy for the past 100 million years. There might also be even younger Cepheids that we haven't seen yet, as these stars would be so bright that they would be saturated in the VVV survey. The fact that we found this thin disk of young stars within the galactic bulge is incredible. We used to think that the galactic bulge was an ancient feature of our galaxy's past, where exclusively old stars had formed separately from the stellar disk. But this finding reveals that things aren't so black and white, and that the formation of newer stars within the bulge could be a natural progression of our galaxy's evolution. But even more inspiring perhaps is a discovery by the Vista infrared survey that lies at the ancient heart of our Milky Way galaxy. In 2016, for the first time, a type of ancient star known as RR Lyrae, another variable star, was discovered in the center of the Milky Way galaxy by a team led by astrophysicist Dante Meniti and Rodrigo Contreras Ramos. This type of star is usually found in globular clusters, which tend to orbit the outer regions of the galaxy. A globular cluster is a tightly packed group of stars that contains tens of thousands to millions of stars bound together by gravity. They're also really ancient, containing a stellar population that can be over 10 billion years old. The team found 12 RR Lyrae stars during the VVV survey, which suggests that they might be the remnants of an ancient globular cluster right at the heart of our galaxy. This finding also provides evidence that might help astronomers to decide between the two competing theories of how nuclear bulges form. While some scientists think that the nuclear bulge forms early in the galaxy's evolution, when multiple smaller galaxies violently collide, others say that it forms gradually over time, where gas is funneled inwards to trigger star formation. Finding these ancient stars here suggests that the bulging center of the Milky Way likely grew through the merging of primordial globular clusters, therefore supporting the first theory. So not only does it hint at our own galaxy's beginnings, but it also offers compelling evidence into how these galactic bulges might form in other similar galaxies. Speaking of ancient stars, VISTA was able to find 2 new globular clusters as part of the infrared survey in 2011. In this visible light image, a known globular cluster, UKS1, can be seen on the right as a hazy red splotch. This cluster had been the dimmest known globular cluster until the new discoveries. Now, compare this same patch of sky, but this time in VISTA's infrared light. Suddenly, we can see what we have been missing. Much more faint than the known UKS1, we can make out a second globular cluster, this time in the upper left of the image, which has been named VVV-CL001. Another globular cluster, aptly named VVV-CL002, was found soon after, and this small, faint group of stars may be the closest known globular cluster to the center of the Milky Way. Did you know that there were only 158 known globular clusters in the Milky Way before these new ones were found by VISTA? For the survey to identify 2 more of these rare stellar objects is quite a significant accomplishment. Within this central region of the galaxy, it's easy for younger stars and cosmic dust to obscure globular clusters, especially since their age prevents them from shining as brightly. But now that they've been revealed, these features bring exciting possibilities for further study. It could just be an illusion of perspective, but scientists have wondered whether VVV-CL001 is gravitationally bound to UKS1. If this is the case, then they would be the Milky Way's first known binary globular cluster pair. We found binary clusters in other galaxies, like in Centaurus A and the Large Magellanic Cloud, but scientists think it might be when these gravitationally bound clusters collide that we get the most massive globular clusters, like Omega Centauri. So studying a binary cluster right in our own galaxy could produce some amazing insights into this process. It's all speculation at the moment, but it's definitely cool to think about. In addition to globular clusters, the VISTA infrared survey identified a multitude of other types of star clusters. At least 96 new open or galactic clusters have been found, which typically contain fewer, younger stars and are much more common than the globular type. Like the globular clusters, they have been hidden by cosmic dust, but VISTA's 4.1 meter infrared telescope has lifted the curtain to show them in all their glory. Take a look at just a few of these stunning images we now have of these objects. One of these open clusters, VVV-CL003, is much more difficult to make out in images compared to the tightly packed globular clusters. Try and see the density differences in the stars in this section of the image compared to the surrounding regions. It was found by Vista 15,000 light years beyond the Milky Way center, and also happens to be the first of its kind to be discovered on the far side of the galaxy. The sheer scale of this survey is staggering. Covering a vast region of the sky and mapping more than 1.5 billion objects, this data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way and beyond. And that's just the tip of the iceberg. This survey will serve as a foundation for future telescopes and observations, which will hopefully be able to expand on Vista's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map that has ever been made of the Milky Way structure and objects, one that unveiled hidden wonders previously beyond our reach, and scientists are already uncovering new galactic features and reshaping our understanding of the galaxy. With the information from this groundbreaking infrared survey, as well as the recent work from ESA's Gaia mission in visible light, it's an exciting time to be an astronomer, and we can expect a flurry of new insights about our own galaxy and the universe as a whole. Vista's infrared observations have unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries where stars are born, and they have broadened our understanding of the formation of our Milky Way. Looking at the sky through different wavelengths has brought about a new era of galactic exploration, and I can't wait to see what else astronomers and data scientists are going to uncover thanks to Vista's 3D map. I'm going to preface this video by saying the universe is a very weird place for us simple mortals. Our lifespans are just a blink of an eye compared to the age of the universe, and things we expect to be constant, like space and time, behave very differently from what you may initially expect. So keep this in mind throughout the video. To answer the question of where the Big Bang originated, I'm going to have to provide some context. The leading theory regarding the beginning of the universe is the Big Bang theory, and without going into all the complicated details, I'll summarize it like this. About 13.7 billion years ago, everything that is in the universe today was crammed together into a space the effective size of 0. At the very beginning, not even atoms existed. It was just a hot and dense soup of fundamental particles. Since the beginning, the universe has expanded rapidly. As it expanded and cooled, atoms formed and stars were born. Now, the universe's expansion combined with the constant speed of light has turned the universe into a time machine. If we look at any region of space, we don't see galaxies as they are, but as they were. Galaxies we see in the foreground are much more developed, forming the more elegant and defined shapes you see here. That is because we are seeing these galaxies as they were only millions of years ago. They've had billions of years to form since the start of the universe, and so they look much more mature and developed. On the other hand, as we look at more and more distant galaxies, these galaxies appear younger. Galaxies that are billions of light years away appear as they would have shortly after the Big Bang, because the light emitted by them has taken that long to get to us. They look misshapen, and there is a lot of star formation going on within them. But in reality, it's important to remember that these galaxies are just as old as ours, and they no longer occupy the location where we can see them. They are probably much further away now because of the expansion of the universe. It is also important to realize that there is no center of the universe, or conversely, that everywhere is the center of the universe. Because it doesn't matter where you are, here or a billion light years away, everything is expanding away from you.
everything is expanding away from everything. Just as a side note though, gravity combats the effects of the universe expanding. That's why superclusters of galaxies exist. And the universe has a filamentary structure. The gravity from galaxies is attempting to keep clumps of them together, even though the expansion of the universe is also pulling them apart. What you end up with are filaments with empty bubbles or voids in between that will only get bigger as the universe expands further. You may have heard of the term the Hubble constant. This is how fast the universe is expanding, currently thought to be around 80,000 kilometers per hour per million light years. So for a section of space 1 million light years across, it expands by 80,000 kilometers every hour. A section 100 million light years across would expand by 8 million kilometers every hour. The current value of Hubble's constant implies that the entire universe is expanding faster than the speed of light, meaning there is a sphere around us that we will not be able to see beyond. Past this sphere, galaxies are moving away from us faster than the speed of light, meaning light emitted by them can never reach us. Everything within this sphere is the observable universe, another term you've probably heard before. We can't see or detect anything beyond the observable universe, which is why we don't know if the universe is infinite or finite. Even if it is finite, it couldn't have an edge and would have to loop around, because, well, the universe is just that, everything that exists. What would be beyond the edge of the universe otherwise? So, we want to know where the Big Bang originated. Where in the night sky do astronomers look to see where the universe started? Well, the answer is everywhere. Because the universe always has been the whole universe. It has just changed in size, from being very small to very big. It doesn't have specific coordinates, because it is an explosion of the coordinate system itself. And this is what shortly after the Big Bang looked like, albeit in microwaves. This is what we call cosmic microwave background radiation, and you can see it anywhere you look into space, assuming you have a space telescope that can detect microwaves, because Earth's atmosphere is really good at blocking microwave radiation. 350,000 years after the Big Bang, the universe was hot, around 2,500 degrees Celsius. Even though this heat would have emitted visible light, we can't see it because the expansion of the universe has stretched the wavelengths of electromagnetic radiation by a factor of 1,000, meaning the photons no longer arrive at Earth as visible light, but rather as microwaves. So, just like seeing those distant galaxies billions of light years away using visible light, we can see what the universe looked like before galaxies even existed by observing these microwaves. This makes this image effectively the oldest thing we have ever seen. Fascinatingly, the slight variations in the image are the precursors to the filamentary structure of the universe you've seen earlier in the video. We are quite lucky in that there are not really any bright sources of microwaves in the universe apart from the cosmic microwave background radiation, which means this view is a relatively uncontaminated view of the universe 350,000 years after the Big Bang. Can we see beyond that? No, not really. Before that, atoms were just becoming a thing, and light couldn't travel through the soup of fundamental particles. So, the center of the universe is everywhere and nowhere in particular. Look at any part of space with a microwave telescope and you're effectively looking at shortly after the Big Bang. Like I said, the universe is weird. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.